My name is Tony Williams. I have the privilege of working at the Royal Society of Chemistry and being responsible for the technical development and implementation of the National Chemical Database Service funded by EPSRC. This is going to be the first of a number of webinars that we will be providing over the next few months. It's hosted by my colleague Jack Gibb, who's presently in the UK. He will provide more data later about when the next webinars will be, but we're going to kick off with Advanced Chemistry Development's iLab, which has been available on the service since the original inception from the Cambridge servers at RSC. It will be presented by Richard Lee, who is from Toronto, Canada, and he's going to show us how we can make use of iLab to access data in their databases. They are highly curated, manually curated databases that have been assembled over many, many years with very careful eyes, as well as their prediction algorithms, nomenclature generation, etc., etc. I won't take all of the steam from Richard. I will let him do the job. I'll put myself on mute. And Richard, welcome to the first audience and webinar for the National Chemical Database Service in the UK.
Thank you, Tony. Thank you for the introduction. My name is Richard Lee. I'm from ACD Labs, and today we'll be going through some of the basics of iLab and how to use the iLab interface to predict some PhysChem, ADME-tox, and other types of properties for various structures. So I'm hoping that everyone can see my screen. And this is the iLab interface. Again, this is a web interface. And when you initially launch iLab, you'll see that we have on our left-hand side the modules that can be predicted. So within PhysChem, if you expand out this category, you'll see our various PhysChem properties. You can do the same with our ADME-tox. We have our toxicity, as well as our NMR predictors, the different types of nuclei that we can predict, spectra 4, and the databases that you can access as well. And lastly, we have our naming module at the very bottom. But first, I'll go through how we import structures within our interface. There are several different methods to importing or drawing a structure within our interface. First, you can either draw in a structure just by simply clicking on this pencil icon, and it will open up a structure editing window. So again, it's something very similar that you've seen before, either with ChemDraw, ChemSketch, IsisDraw. Again, it's just various tools that you can use to draw structures. Another way is to use our dictionary. So within our dictionary, we have over 160,000 names of compounds. So you can simply type in a name. So let's say acetaminophen, and again, aceta. And you'll be able to just type in the name and select the structure. Another method is to, if you have a file, so a mol file, ChemSketch file, CDX file, you can browse your computer and upload that particular file and just upload it, and then it will appear within this ChemSketch or this structure interface window. We also have the ability to just copy and paste from a clipboard. So if you just want to copy and paste directly from ChemSketch, IsisDraw, ChemDraw, or any other tool or drawing tool, you can do so. Or we also have the ability to submit SMILES notation. So you can just copy and paste your SMILES string, and you'll be able to it'll be able to generate that structure based on the SMILES string. So there are a few different options to getting the structure into the iLab interface. I'm just going to use the dictionary for now. I'm just going to use acetaminophen. And once I have the name in, I'm just going to click on name, acetaminophen, and just select the option. And now it will bring up the structure. And as soon as I do so, it will generate a few of the physicochemical properties. So on the right-hand side of the structure, we'll have some basic molar refractivity, molar volume, index of refraction, some Lipinski-type properties already calculated for you. We also have some MS-related properties with regard to monoacyclic mass, what the masses should be observed in, let's say, electrospray or positive mode, negative mode, etc. If you want to look at specific PhysChem modules, this will be the time to expand out the PhysChem properties window. And now we have listed the various PhysChem properties that we can calculate. If we click on log P, you can click on that. And now it will try to calculate our the log P value. And again, the algorithm that is being used is what is actually being used in our desktop software. So again, it's as sophisticated as what we normally put in our desktop software. So in our log P module, you'll notice that we have 5 different structures that it's actually using to calculate the predicted value. So we have the log P from ACD Labs, as well as we have another value, which is log P from pharma algorithms. So we have 2 different predicted values. And both are using the top 5 structural candidates within our library. So it uses the top 5, it looks at the structure, it looks at the top 5 similar structures, and it will predict that value based on the top 5 structures that was been able to retrieve. So if you hover over the actual report, it tells you exactly what it's been calculating. It's calculating the octanol water partition coefficient, and this is using pharma algorithms 2.0 version. If we click on or just hover over the log P for ACD value, this is what it's using with regard to the log P calculation using the ACD lab. So it's using the octanol water partition coefficient using the ACD lab algorithm. If you want some more information with regard to each module, there is a help icon here to get some more information. If we click on that, it'll give you some more information with regard to how many structures are in the database that it's searching for, and gives you some more information with regard to how the predicted value was calculated and what type of internal validation sets were used. So if we look at the log P modules, it uses a training set of about just over 11,000 compounds, and it used about just less than 5,000 structures for a validation set. So it is fairly robust, and with that regard. If we go to general structures or general usage, it basically gives you some information with regard to what each pane is describing. So if we go into number 1 is located as a tree view for the modules. 2 is the structure pane, etc. Again, once you have these properties calculated, what you can do is you can click on Download Report. So you can either save it as a PDF file, or you can save it as an Evernote file. So if we click on Download Report with PDF, it will actually generate a PDF file for that particular property that you've been able to calculate. So again, just a PDF file that you can save and print out, and it gives you the listing of the top 5 structures that it's been able to use for its calculation. So moving on, if you wanted to look at, let's say, the database. So for instance, I'm going to go look at the log P database down here. So this is where you can specify a bit more of the structures that it's actually using to calculate the log P. Within our database, you have the ability to search for the exact structure right now, has come up with this structure, or if you want, you can have the ability to search for similar structures and similar or substructures. As well, you have the option to specify the molecular formula if you're looking at similar structures. So example, you can go to look for compounds that have carbons 1 through 25, H 10 through 25. So this indicates that it'll look for compounds that have 1 to 25 carbons and 10 to 25 hydrogens. You can also specify with regard to molecular weight, as well as log p-values. If you have a specific reference, that name that you want put in, you can put so in here as well. Or if you have the name of the structure. So if I just go to similar structure and click on search without any constraints, it will look through our database and pull up the top hits. So at this point, it's been able to come up with several candidates. And what you can do is click on the entry. So for instance, I'm just going to click on entry 4. And what it will do is it will bring up the structure, but also give you the reference value as well as the actual reference itself if you want to go back and look up in literature what the reference is. So in this mode, you're searching through our database. So you can do the same for solubility as well as pKa. If you wanted some more information with regard to some ADME-tox properties, and this is the structure that you still want to search for, click on ADME. And again, these are all the available modules that you can use to predict. So if we go look at the log BB, which is the blood-brain barrier, it gives you some information with regard to the fraction bound. It's bound in plasma, as well as if there is a value for it. If we go to BBB, this predicts whether or not how well it's going to cross the blood-brain barrier. In this case, these are all the compounds within our database that it's using to train the BBB value. And the blue nodes in this case represent those that can cross the central nervous system, and the red is where it's these are inactive, CNS inactive. And again, this line represents the more or less a line that differentiates between the two. So again, we can go on and look for different ADME-tox properties. So again, if we look at the glycoprotein substrate specificity, it gives you a more of a qualitative value. If we look at the toxicity modules, we can look at the Ames test, and it gives you a fairly high positive Ames test. And again, if we hover over it, it tells you what it's gives you a short description of what it is. And again, if you want some more information, you can click on the Help menu, and it gives you some more description with regard to how these values were calculated. Now, if you wanted to look at some predict NMR structure or spectra, you would go into our NMR modules here. So within our software, or within iLab, you can predict carbon, proton, fluorine, nitrogen, and phosphorus NMR. And this uses the same prediction engine that's found in our desktop software. So if I click on proton NMR predictor, what it will do is it will use our prediction engine and generate a predicted proton NMR. So if I just hover over a peak within the NMR spectrum, that will highlight the proton that it's been able to specify. And if I keep moving my cursor over the peaks, again, highlights within the structure as well as the tables which atom it is and the coupling constants that are associated with it. Now you also have the ability to switch views. So if you want to show chemical shifts, just simply click on the shift icon here, and it gives you a more specific chemical shift value. If you want to show the atom numbers associated with it, you can click on the atom numbers as well. Again, you can zoom in on a region just by simply left-clicking and dragging across the spectrum. And you can see some of the splitting that's been able to predict as well. Now again, you can use these icons and tools up here to change the view. So if I want to just look at the full scale, look at the entire spectrum, I simply click on the full scale. And you can also download the predicted spectrum as a JCAM file, or again, you can download the report as a PDF. Open, and it will open up the PDF with the structures, the compound name, the calculated spectrum, as well as the shifts and the coupling constants, as well as the associated errors. Again, you can do that for the carbon if you wanted to. If you want to have both sets for carbon and proton, you can predict both. Aside from prediction, you can also look at look through our extensive NMR database. So if I click on hydrogen or proton NMR DB, we access the NMR database. So again, it's very similar to the Physichem and AdmeTalks databases that you can access. With regard to, you can set the source, the year, the volume, the page number with reference. You can reduce or specify the criteria with regard to how large the compound you want to search for. If you're looking for similar structures, again, you can specify how large the compound is, how many carbons, how many nitrogens, how many protons, molecular weight. If you want to look at coupling constants, or the name itself. So again, if I click on search without any of the restrictions, it will go through the database, and it will pull out the top candidates within the database. Now we're just populating the table. So again, we have several within the database. If you click on, let's say, the first one, you can see the predicted, the chemical shifts within the reference, as well as the coupling constants. Or this is the proton and this is the carbon. And also, you can see the reference that it's been able to retrieve that data from. So you can do that with the carbon database, the proton, the carbon-proton database, fluorine, nitrogen, and phosphorus as well. So again, these databases are updated, I believe, quarterly. So so they are consistently updated with as many references as we can retrieve. Within our naming tool, you can generate the IUPAC names from the structure, or you can generate the index name. Again, you have the ability to generate a name to structure. So if you had a name, you can put in the name, and then it will generate the structure for you. So as you're using iLab and you're looking through a number of different structures with varying phys-chem properties, what you might want to do is look at history. So when you go in and out of iLab, you actually have the ability to, iLab has the ability to store your previous searches. So if we click on History View, it looks at all the predicted modules that you were looking at, and it gives you a timestamp. So I can look at, if I go back to page 3 of my records, I can look at log S of this particular compound, and I was able to look at it back on June 28th. So if I click on that, it will retrieve that particular predicted property. So it's a nice way of going back into the history view and looking at all the structures that you've been able to search, and retrieve some of the phys-chem properties that you were looking at without going through and drawing the structure and going back and predicting the phys-chem property again. And again, all this can be, any of the properties and predicted values can be exported as a PDF or as an Evernote file that you can look at offline. I think that is all that I want to show.